Hello, my name is Alex Izquierdo, and I did my capstone project on mapping seagrass, taking a visual approach to conservation research, sort of seeing conservation not only as a series of academic works, but also as a visual stimulus. So for the introduction of my capstone project, seagrass species as an ecosystem driver are vitally important to a wide variety of organisms, including manatees, species of fish, crustaceans, as well as turtle species like you see in figure 1 down here, the green diamondback terrapin of the Chesapeake Bay, who relies on seagrass for food, shelter, and survival. However, though, seagrass species are in constant decline for a wide variety of reasons, including dredging by boats, coastal development, warming ocean waters, etc. Because of this, the IUCN Seagrass Specialist Group categorizes species of seagrass and attempts to get up-to-date conservation data, whether this be outsourcing to other researchers or doing their own research in the field. One way we can look at conservation data is by mapping, and a great way we can do this is through GIS technology. We can map locations of seagrass to see conservation visually. So my research questions come into this capstone were how can we utilize GIS mapping tech to identify hotspots of concern and optimism for seagrass conservation, as well as how can these results be used to prioritize areas for targeted conservation and restoration. So my methods, like I said earlier, I interned with the IUCN and their Seagrass Specialist Group. First of all, I discussed logistics with researchers, the first one being Dr. Alyssa Novak at Boston University. She gave me a really good scope of what the North Atlantic seagrass composition looked like in figure 3, 5 species were present, as well as giving me some really good advice as to how to categorize the data from the articles. Additionally, I contacted Dr. Porsandias in Greece, who's a big advocate for visual conservation data, with his focus being remote sensing, but he gave me some really good advice with GIS technology. So to start off, I collected and categorized data on seagrass beds from all over the world, from about 300 or so articles for bioregions 1 and 2. I categorized the data, for example, in figure 2 by the source it was taken from, the location, the country. This is the latitude and longitude, and the species, as well as the year it was derived. Through this, I was able to construct 2 GIS maps for bioregions 1 and 2, figures 3 and 4 on my presentation, to highlight areas of optimism and concern for seagrass conservation. For the results, both regions in doing this map, I found featured areas of optimism and concern. For example, in the Spain region down here, Portugal, a lot of seagrass plots were recovered. On the flip side, in this northern UK region, not a lot of seagrass. The North Sea, as well as Poland, is the same thing. So seeing the disparity between the two is one big highlight that I found in doing this project. Another result that I found was the identification of intriguing species that shouldn't be present in a specific location. For example, the Rupium ridima in figure 5, it's only present in this Chesapeake Bay region in a 10 or 15 kilometer region for hundreds of miles to the northwest, east, and south. So seeing those interesting species come to light, building these maps was something that was really interesting to me. The final result was I successfully helped the IUCN update their databases, really categorizing their data and setting a good benchmark moving forward to finish the rest of the 4 bioregions of the world. So implications of this research, I feel like, are not only for seagrass conservation, but also for conservation research in general. This is because a lot of species do depend on seagrass for sustenance, including fish species all over the world. They feed on crustacean species that live in seagrass beds, as well as harbor their eggs. So when human populations depend on the fish species and the seagrass beds degrade, it causes this cascading troph that leaves a lot of people around the world undernourished, which is sort of a shame. Another implication of this research is researchers can use this information to draw conclusions and show gaps for needed funded research. For example, in figure 4, the Costa Rica region heavily researched because my contact from bioregion 2, Dr. Stanford, works out of Costa Rica, but like you see in these areas of Honduras, Nicaragua, very under-researched, likely because they're very rural and it's hard for Dr. Stanford to get out to those regions. So getting a more holistic view, putting the puzzle pieces together, so to speak, is something I would love to see in the next coming research. Additionally, another implication is peculiar species can shed light on environmental and biological abnormalities. For example, in figure 5 with the Rupia, what is it about this area that causes such increased rupium marinum growth, a traditionally warm water species, as opposed to the species that should be present, the zoster marina. So what's next? I feel like there's a couple things that I would love to see in this research moving forward. Firstly, I'd love to see all 6 bioregions categorized. I feel like that'd be a great accomplishment and benchmark moving forward. If you could get all 6 bioregions categorized by 2021, you could look back over the decades and use 2021 as a resource. Additionally, I would love to see more research in a temporal nature, meaning time change over time. For example, you could see an area with, let's say, about a 50% decline in seagrass and the surrounding areas of 20 or 30% decline. What is it about that region of 50% decline that is causing such degradation for seagrass? Sort of pinpointing that and doing further research, I feel like is crucial. Additionally, this could lead to new mitigation techniques for not only seagrass, but also for organisms that depend on seagrass, sort of leading a cascading trope of conservation through this pinpointing of degradation of seagrass. For acknowledgements, I would love to thank my advisors in this project, Drs. Sullivan and Rusink, as well as my family and friends and peers. Drs. Rusink and Sullivan gave me total creative control in this project, which is amazing. They're always a shoulder to lean on whenever I needed advice, so I couldn't have done without them, as well as my family, friends, and peers in the cohort. You guys have all gotten me to this point, and I'm really thankful, so thanks.